Good afternoon, everybody, and thank you for being here also today. This is the 7th webinar organized by provoke. By now, we are close to the end. Next Thursday will be our last appointment. I'm clearly sad about that, so I hope that you don't miss the last one. My name is Stefano Gagliotto, and I'm the Chief of Sales here in provoke, but today I will be the moderator. We will have a section of about 30-40 minutes for the presentation. In a second part, about 30 minutes reserved to the questions that you are free to do anytime using the Q&A tool that you can find the bar at the bottom of your screen. As usual, all the material, video, and presentation are available in our website, progold.com, in the webinar section. The title of today's work is Tarnish Phenomena of Silver, Chemical Interaction and Analysis Methods. So today we are going to talk, after several appointments dedicated to the goal, about silver and a very serious problem concerning this metal as well. The speaker today is Patrizio Sbornicchia. He is with us for many years. Let me say that he is our tautologist. He is graduated in chemistry and got a PhD in materials engineering with a specialization in regarding investment powder. He's a great expert in this matter. He attended at many jewels courses and has been also teacher at the Jewels Master in Valencia, which is one of the districts for jewelry production in Italy. So I think that we can start. I said all, and I can pass the word to Patrizio, wishing everybody a good listening. So Patrizio, you can go, and good luck.
Thank you. Good afternoon, everybody around the world. And thanks to Stefano for his warm introduction. Yes, today I shall tell you about sterling tarnishing, a phenomenon known since the dawn of time and entered about 1 century ago into metallurgy research that often does big efforts to defeat it, or at least to reduce it at the minimals. This phenomenon basically consists of a natural oxidation of silver caused by sulfur that darkens the beautiful luster of this metal and spoils its whiteness. But also other alloy elements can be affected by and influenced by several factors, such as acidity, as you can see from this first chemical reaction, but we could write additional reaction that show you the influence of other parameters like oxygen, humidity, temperature, and other pollutants. The wide number of these factors makes difficult the complete understanding of this process that nowadays is just evaluated by the repeatability of a comparative and visual method on the basis of chromatic changes. But it's lacking of a quantitative procedure that shed lights on the surface chemistry, indeed. Currently, the homogenized sterling undergo to an accelerated test being surrounded by hydrogen sulfide atmosphere produced from the floor by vaporization of very dilute ammonium sulfide solution and with controlled condition of temperature and humidity into a climatic box. This climatic box has a transparent wall in order to follow the color changes as a function of time of the metallic discs. Those are hung from the chamber ceiling by means of inert wires. The tarnish resistance is definitely evaluated by visual comparison with respect to the starting color. In other words, we were inspired by and diluted the aggressivity of the corrosion test ISO 4538 with thioacetamide. These trials were additionally integrated with other two separated stressing tests. The first one is an ultraviolet radiation, and the second is heating at high temperature in order to include more complicated environmental interaction encountered in the real life. Amongst the tested alloys, we see as a former material a traditional sterling with the 9/30,000 of silver and the copper balanced alone. Even we all know that historically the official sterling assay is fixed by law at 9/25,000. And the second sample is pure silver. Both of them taken like experimental references. The third alloy is a special silver-plated sterling having particular anti-tarnish additives inside the galvanic coating. And the last is our commercial alloys with zinc and other elements functional to the tarnish resistance. By using a digital spectrophotometer to measure the color variation with respect to the starting hues and following the CLA procedure that was extensively described by my colleagues during previous webinar, the averagely most resistant alloys was silver-plated sterling silver and commercial alloys as depicted by the red and the blue components shift along the ordinate axis as a function of time. And this was also confirmed by luminosity variation and overall chroma variation that simultaneously contains the three information to define a tint inside the color space, such as luminosity, red and blue components, already watched before as separate attributes. Usually, just to give you some idea of the figure's magnitude, usually DE less than 1 is hardly appreciable by naked eyes. And after sulfidization test, values under 4 can be still considered almost tarnish-free. So additionally, in order to extend the study toward more real and complex conditions, the effect of sunlight on sterlings was simulated by ultraviolet irradiation and performed into a xenotest machine set with a power of 1.4 kilowatt at 60 Celsius for 4 days in natural atmosphere. With a quite different result, because sterling silver this time showed the lower color difference, together followed by commercial alloys. Counterwisely, the pure silver and the silver-plated sterling showed the highest color damages under ultraviolet beams. And finally, to complete the study, the effect of the temperature on the alloy has been evaluated by heating the disc at 700 Celsius in air for increasing time, up to 6 hours, and examined under scanning electron microscope and by means of plasma emission spectrometry to collect morphological and elemental information and having a closer understanding of real phenomena. The electron microscopy of heated sample at high temperatures has revealed, in the case of traditional sterling silver, the preferential transformation of the regular eutectic structure into a spongy copper oxide surface after 6 hours. For instance, whereas in the case of pure silver, as it was reasonably expected, We obtain a coarser grain microstructure after thermal treatment, and then keeping the very good surface quality of the starting polished condition. Interestingly, the silver-plated sterling, after thermo-oxidation at 700 Celsius, showed one heavy damaging of the silver coating with the formation of porosity, grain coarsening, and roughness increase that led to light dispersion and reducing reflectivity if compared with the near flawless situation of the initial sample. And another surprising result came from commercial alloys, where the thermo-oxidation test provided the formation of very silver-rich islands around the copper-rich phase. This island can be also considered almost pure silver. After all these treatments or sample preparation, the chemical analysis was performed by using glow discharge optical emission spectrometry that uses an argon plasma as atomic exciting source like ECP technique. And at the same time, for sputtering and probing into the deep like a sort of three-dimensional analyzer. This technique is able, for instance, of pitting rate of about 700 nanometer per second and sampling depth of 5 to 50,000 nanometer, or if you prefer, 50 micrometer. But unfortunately, is a technique not sensible to molecules. Now, before scrolling through the results of each alloys, I shall give you a brief explanation of the analytical response from such a kind of instrument. Each curve with different color belongs to a specific chemical elements. Along the abscissa axis is reported the appearing time of the signal, or rather the depth from which it came from. Whereas the ordinate axis reports the signal intensity, and it is proportional to the element concentration. Now, we can start with the glow discharge analysis for polished traditional sterling silver after a few days in air. It showed only traces. I'll provide you some magnification, but it's difficult. Okay, I cannot magnify. It showed only traces of surface sulfur, oxygen, and hydrogen, revealing the important role of humidity in this process, and some oxygen and hydrogen in the underneath layers, probably residues of the sample preparation. The same sterling alloy, after 4 days into xenotest machine, showed a relevant increase of surface sulfur coupled with silver and oxygen and hydrogen, revealing the important catalytic action of ultraviolet light. Important is that also copper is almost absent onto surface, as you can see here. Instead, the sulfidization test into humid chamber enormously increases the sulfur concentration onto surface of sterling silver, And copper is also sensitively increased. As you can see from this mild peak within the big spike of sulfur, the copper is slightly higher than its nominal content in the alloys. On the other hand, the thermal treatment cannot increase the surface sulfur so much, probably for sulfide decomposition as for roasting at high temperature in ores process. But the developing of copper oxide in the air is very visible. On the other hand, silver oxide is penalized because this compound is very instable when heated. If I remember correctly, the silver oxide starts to decompose around 200 degrees Celsius. Pass now to the pure silver. Its behavior produced results similar to sterling silver, with traces of sulfur, oxygen, and hydrogen onto the surface, and some oxygen and hydrogen from manufacturing process in the underneath layers. Similarly to sterling silver, but in higher extent, pure silver developed a strong concentration of surface sulfur under ultraviolet radiation. And once again, the presence of oxygen and hydrogen traces onto surface always proves the important key role of humidity in this passivation process. The direct sulfidization test on pure silver showed a high presence of surface sulfur, higher than its corresponding xenotest, but lower respect to sterling silver, probably for the absence of copper in the metal, which has a crazy strong affinity for sulfur. The thermoxidation of pure silver probably led to the surface formation of silver compounds more complex than simple oxides, because they are thermally unstable, as I told you before, over 200 Celsius. So with the likely formation of silver sulfates much more stable, and the higher oxygen content under the surface may depend on the strong diffusivity of this gas over 400 Celsius. All of us know the incredible capacity of silver to dissolve extraordinary amount of oxygen, especially at the molten state. In the case of silver-plated sterling, left resting in the air after simply polishing, the first clearly visible aspect is the decreasing of silver by trespassing the nearly pure galvanic coating and the presence of sulfur and hydrogen and oxygen inside this galvanic coating. And lastly, the presence of this pollutant also in its surface. Ultraviolet beams onto silver-plated sterling always lead to a big concentration of surface sulfur together with a significant presence of oxygen and hydrogen at the surface, and traces of them into the galvanic coating. The direct sulfidization into climatic box for silver-plated sterling surprisingly gave lower sulfur concentration respect to ultraviolet test, though relatively high, revealing anyhow the protecting action of the anti-tarnish additive into the galvanic coating. Here from Xenotest, the values was about twice, for example. And the thermal treatment at high temperature for silver-plated specimen provided no additional information regarding this phenomena, except for sensitive degradation of the galvanic film, displaying the interdiffusion of some silver, copper, and oxygen between the surface and the bulk. Now we come to the commercial alloy. Also, the polished commercial alloy gave no different result respect to other simply polished sample left in air, as you see before. But in the case of ultraviolet radiation, the commercial alloy provided a surface sulfur lower than pure and silver-plated sterling. And this is very interesting, even if the sulfur is quite high. So we could say that the alloy elements into the materials seems to provide one intrinsic protection against ultraviolet beams. Moreover, again, copper seems to be not relevant on the first layer in the surface. Contrarily, the directly sulfidization test in the climatic box provided a less sulfur concentration respect to traditional sterling, proving again the protective action of the other elements in the alloys, like zinc, silicon, etc. Then it provided the same sulfur content respect to pure silver and higher sulfur concentration respect to silver-plated sterling. And similarly to sterling silver, the commercial alloys at high temperature undergoes to copper oxidation, as you can see from this relevant peak, also at the expense of silver onto surface that is decreasing. Now, by summarizing some general results of this research, we could say that sulfur damaging is more severe for the silver-plated sterling under ultraviolet test, maybe due to damaging or photo degradation of the anti-tarnish additive onto the galvanic coating. Whereas the direct sulfidization into humid box seems to be more aggressive respect to simple traditional sterling, probably for the sole presence of copper having one amazing affinity for sulfur. Regarding the effect of humidity, for traditional sterling, it seems that low water vapor concentration like those inside the ultraviolet chamber promotes the sulfidization of silver element alone, whereas high humidity conditions like those into climatic box can lead to the sulfidization of copper and silver at the same time. Then, by concluding, we can say that always controlling the experimental condition, like temperature, humidity, sulfur atmosphere, as usual in a scientific work, the tarnishing phenomenon can be quantified in a more objective manner if the optocomparative and empirical procedure is supported by analytical instruments for the color measurements and for the surface and depth chemical profiling. Thanks for your attention.
Oh, thank you so much. Thank you so much, Patrizio. This topic was a little bit technical, but Patrizio tried to explain in a simple way. So thank you very much. I remind to all of you that for any further information, if you want to go deeper in this topic, you can write. You can see in this last slide our email addresses. So feel free to ask us whatever you need. And if you want to better understand or if you want to go deeper in any topic, feel free to write us. We'll be happy to try to answer you. So we will try now to go with the Q&A section, Patrizio. So I can give you already. So Chintan is asking this, Patrizio. Do you think that using sulfuric acid for pickling affect tarnish on silver articles, as we think sulfuric acid is little aggressive? Do you suggest an alternative chemical to do pickling avoiding sulfuric acid?
In general, sulfuric acid can dissolve in part silver and copper, but the compounds that are formed are quite soluble. So if you rinse the cast items very well with distilled water, you should not have residual salts, and the tarnish of pickling in this way should not be helped.
Okay, thank you. And Marcus is asking, so when our items, okay, are displaying in our showrooms, and where there are some halogen bulbs light, okay, in those showrooms, which may accelerate the tarnish on silver items, what do you suggest? How can we minimize this effect, or is there any other way to overcome such problem?
So for humid tarnish, as we can see before from the slide, it's possible to apply galvanic coating. But I don't know if there are in the market some anti-tarnish additive for ultraviolet protection. I don't know. Honestly speaking, I don't know.
Okay. Do you think, oh no, this is another question by Chintan, okay? Do you think that the tarnish effect depends on the way the jewelry item is produced? If, I mean, if it is produced by investment casting, or if it is produced by mechanical working, is there any difference?
Excuse me, I didn't get you, Stefano. Can you repeat the answer?
Do you think that the tarnish, okay, can have an effect if you are producing items by investment casting or mechanical working?
Okay.
Any difference? according to the process applied?
We can say that the more homogenized is the alloy, and in general, the less is the tarnishing, because the microstructure is more uniform and there are not local difference in chemistry, less segregation. So in general, I feel to say that plastic deformation production, or deformation, if you prefer to say in this way, are less prone to tarnishing.
Okay.
Speaking about the same chemical composition for the alloys, of course.
Okay. So Marcus is asking, so do you think that there can be really anti-tarnish alloys available in the market? Or is it just a marketing words, anti-tarnish? Or rather it should be delayed tarnish on real terms using a good metal? What is your opinion?
If I well understand, the question is relative about the existence
of a real anti-tarnish alloy in the market.
In the market. So, as in the past Italian section, we have to say that this kind of alloy is not yet existing. So, we don't have a perfectly anti-tarnish or tarnish-free alloys. We can just only retard the tarnishing in a little extent. So I feel to say that there is not a particular alloy against tarnishing phenomena. It's a natural reaction that we cannot stop. In any case, we can delay the darkening of the surface, but we cannot stop this reaction so far. Maybe in the future, who knows?
Okay, I think this is a kind of nickname, and RY is asking, what about the rose gold? Is it the same process in terms of the problem of silver, and is it possible, and in case how, to prevent tarnish phenomena at rose gold?
As I told during the presentation, copper has a crazy affinity for sulfur. And in low caratage alloys, tarnishing can happen slowly or slower respect to silver, but happen even if it's one golden alloy. Can be quantified in the same way like silver, using humid chamber with color measurements and chemical surface analysis. Yes, for low caratage, rose, red, gold, tarnishing is a real phenomenon, a real problem also.
Okay. Marcus is asking that the alloy that we use, that supplier are gonna say they are anti-tarnish. When we cast at higher temperature, all pieces cracks. Does it mean the element that you use in anti-tarnish can cause crack at high temperature in investment casting? The metal does not, okay, whereas when we use a basic copper and zinc alloy, the metal does not crack even if we cast at higher temperature. So you understand the question? Maybe I also better explain you, Patrizio. You get the meaning?
So the problem is with our commercial alloys that I showed in the presentation.
No, the question is this one.
Mm-hmm.
So the elements, because he said that when you cast a high temperature using
Mm-hmm.
the alloy anti-tarnish, maybe inside there are some specific elements that maybe can cause cracks.
Ah, yes.
Is it true, or can you tell something about this?
Yes, yes. There are some concurrent alloys also that have some particular elements that enlarge the melting range of the alloy so much that during the cooling of the material inside the flask, some liquid part of the alloy can remain also before quenching and can give cracks. Yes, under quenching. Yes, it depends from these specific anti-tarnish elements that modify the melting range very high.
Okay, Mr. Ravi is asking, is there any way to apply thinness liquid layer like resin on silver to prevent or avoid having atmospheric or environmental effects?
Yes, this is true. This is already done from long time. For example, in furniture metallic object. This is only simple acrylic resin, for example, that avoid the contact of the air with the metal surface. For example, in the case of brass or bronze, you can apply this special solution by spraying on the surface, and this produces an hardening coating, polymeric coating, that protects from the atmospheric pollutants. Yes, this is also possible for silver, but differently from a table made in brass or a statue made in bronze, you have to wear this jewelry, and wearing imply friction with the skin, with the perspiring. So this barrier, polymeric barrier, is not so resistant. It will last few days, I think.
Okay, thank you. Daniel is asking, when we leave for, let's say, long time silver items in the storefront, inside a shop, okay, for a long time, and the colors start changing, okay, becoming black, let's say, can we consider it is oxidation or tarnishing?
When you see some items into
After
glass,
a long time in the storefront is vitrina, or a shop,
okay,
okay, for a long time, okay. And is it oxidation or tarnish? And can you explain me the difference, please, in short way?
So it's a matters only of technical definition, because tarnishing in very theoretical words can be physical or chemical. Okay. In the physical way, you have just some substance that cover without react with the base metal. In the chemical way, you have something in the atmosphere, in the surrounding environment that react with the metal alloy, producing often producing an chemical reaction of oxidation. Okay, the oxidation can be performed by different elements like sulfur, oxygen, chlorine, fluorine, but also by physical media like temperature, ultraviolet light, and so on. So I don't know if I replied correctly to the answer. In any case, tarnishing is everything can spoil the luster of the luster and the whiteness in the case of silver of any kind of metallic surface.
Okay. Okay. So Mr. Vagesan is asking, so how to find out early stage of tarnishing in silver? Can the silver be sterilized at that time? I think that the meaning is if you can prevent, okay, in somehow, if I'm well understanding the question.
I was thinking sterilization about something that destroys bacteria over the surface. Sterilization in what sense?
In fact, okay, you can try to answer in somehow in both the way, and in case if it is not clear, Vagesan, please send me another comment, okay, being deeper, okay. So if you want to say something, Patrizio, in the meantime, we will wait if there's a reply.
I can try one answer if you want. If you mean sterilization as cleaning, it is enough that the items are very washed, rinsed with very pure solvents. Can be pure water, pure organic solvent like acetone, alcohol, in this way. In order to polish away any traces of something that can change the reaction with or enhance the reaction with the environmental pollutants. In the other sense of sterilization, if you mean that the sterling silver must be clean from any kind of bacteria, or this is the age of virus, yes, also bacteria can increase oxidation because during their living produce sulfur and other oxidant debris. So sterilization with water steam can be advisable.
Okay. Jamie is asking if tarnish phenomena, how the tarnish phenomena can change according to the different environment where you are. Let's say mountain, humid, dry place. How, if it is it changing, and if you can manage it somehow?
It's something that we are studying. We are still studying in these years. It is not simple to say. There are tens and tens of possible chemical reactions. For example, starting from the presentation, the sulfur source can came from human activity, but also from natural geological activity, from volcanoes, for example. But that is not the sulfur the only causes of the tarnishing. For example, oxygen, chlorine in the swimming pool, or also organic compound inside the soaps, domestic soaps, and so on. There is an infinite list of things that can produce tarnishing. It's not easy to. The only thing we can say is that any kind of chemicals that can oxidize, that succeed to oxidize the elements, chemical elements or metals inside the alloys can produce tarnish. So silver is more noble than copper. Copper is more noble than zinc. But even if the copper and zinc are less present, are lower in content in the alloys, in any case, they can produce tarnish. Also, if their concentration is very low.
Okay, so Mr. Wagesen is, you remember before in the question before we were talking about way to sterilize silver. Okay, so he had something asking. So his meaning was to ask if there's something that we can use to prevent this phenomena.
Okay.
If so, there's something, yeah.
So a way to prevent tarnishing.
Yes, yes.
Okay. So the tarnishing can be prevented better, reduced, honestly speaking, okay? Reduced by the use of some specific anti-tarnish elements or additives in the
whatever is your opinion to prevent, if you have any suggestion.
This can be the next research for our company. It's okay. It's know-how. It's a secret. Yeah, I can say something about what is already done in the market in the research. For example, there is the addition of some specific element that produce a thin film on the surface that reduce in a little extent the contact with the darkening silver or darkening copper with the atmosphere. And there is also the good solution to make a galvanic coating with anti-tarnish additive, because only galvanic coating, as in the past, is not enough to protect the sterling silver. But this coating, this galvanic coating, must contain some special additives to have an anti-tarnish effect, to reduce. But if you go in the thermal station with the high sulfur concentration during holidays, no anti-tarnish coating can resist to tarnish, to oxidation of sulfur, high concentrated sulfur, like in the thermal station.
Yeah, in fact, Patrizio, there is also the last question by Alessio was connected. In fact, he was asking if there is using any chemical anti-tarnish product, that the one, for example, that he used for red gold alloys, if he can use to prevent this phenomena. So if generally there is something that you can use to put up both just to try to avoid a problem.
Okay. I am not very sure about that, but if I well understood the question, my friend refers about a coating or something inside some specific elements inside the alloys.
Maybe both, but okay. Mainly the question was referring regarding some coating. Exactly, he told me right now.
I'm not sure about that, but I think in the market there are some particular organic coating that can help to increase the lifetime of the beautiful luster of metals. Should be.
Okay. Thank you very much, Patrizio. Looks that there are no more questions. I take chance to remind you, giving time if you want, if somebody wanna add some other question, to remind you that next Thursday we will have our last webinar, and we will talk about 3D printing jewelry. It is important because the speaker will be one of the member of the board, Luigi Benetti, so we are happy for that. So I hope that you won't miss it, the last webinar. And I also would like to tell you that we are already organizing new sections that are coming. So I hope that next week we will be able also to tell how we will organize our next steps and the job that we are going to organizing for the next months. Thanks to everybody. Thank you very much. Question no more, Patrizio. Patrizio, thank you very much. And thanks to all the attendees.
Thank you too.
Thank you. Take care and see you next week. Okay. Thank you.
See you again. Bye.
Bye. Bye.